everybody. Thanks for having me. I'm one of the founders of cortical.io. Our focus is to work in the field of natural language understanding, sort of one of the disciplines of AI, in some ways a bit particular or different from the more number-oriented model building. But it becomes more and more important, as I will show. So the title I gave to the talk, High Efficiency AI, is meant to be seen in contrast for the traditional, I would say, goal that we have to get more and more precise systems. The point I want to make is that actually not precision is the enabler for actually deploying functioning systems, but it's actually the efficiency. And the reason why this is very obvious. We are just experiencing a real explosion of data. So we are currently in what can be called the zettabyte age. That's basically, in terms of numbers of bytes, that's 1 with 21 zeros. So this is incredible amounts of data, and it has been accelerating the way how it comes in. And what is interesting is that the biggest part, I would say, right now at least, seems to be the human-generated files. So everything that starts from email to documents to social media, for example, is of course becoming a bigger and bigger part in this. And what is specific to this is that it actually is text data. So it's the expression of opinions or knowledge or needs of people. And it's increasing so rapidly that we probably need to actually automate this to keep up with it. And for that, of course, we have to understand what a piece of text or a message or an email actually is about. So the problem we are facing, on the other hand, is that as the amount of text data increases, we are nevertheless, from a technical point of view, on a pretty much stagnating performance on the basic computers or processing elements. So since quite some time, the improvement has not, as it used to be, doubled from one release or generation to the next, but it became sort of stable at the granular level, and the actual increase of performance could only be done by adding more computational power to it. And as a consequence, what we see is that we gently but steadily lose, if you want, productivity in the context of that data. So we will have actually to find a way to work around this. So the one of the two reasons is basically the very classical von Neumann computing concept, where you have in a computing unit a part which is sort of the processor, and you have another part where the actual data is stored. And the bottleneck, in fact, is that we actually have to shift and shuffle around data and commands through a tiny little bus that can barely keep up with this. So that's sort of an architectural problem that we face in the first place. And interestingly, I mean, that architecture, we are using it now for many decades. And the best we could come up with, in fact, other than getting more transistors into it, is to have more of these processing units. But of course, there is always the next level of bottleneck when it comes to the communication between those clustered units and so on. So that's a sort of a built-in constraint that we have, where we think we have to overcome it to become sort of freely scalable again, and to be able to reasonably efficiently grow with the growing number of data and more need in this. The second level is, as I would say, at the machine learning approach per se, which sits on top of this von Neumann issue that we saw. And so this is here a very generalized model, and of course there are many flavors to it, but at that point I would just want to sort of see that from a very high level to get a feeling on in what context those systems are embedded. So when we do machine learning, basically we want to transform some data that flows into some useful data that goes out of it, and we want to do this because the processing would be extremely complicated to do by sort of an analytical way. So trying to understand the problem and figure out all the formulas that you need to actually generate some useful output. So there are, as we know, a lot of problems that we cannot design systems that way. So we started to use actually data to have the computer find itself how the transformation has to happen. And that happens, of course, based on training data, which typically is supposed to show the system how to transform particular examples from an input to an output. And the efficiency of that model basically tells us how much of that training data will we actually need to get to a model that works reasonably well for such a transformation. And the limitations that we see here, we see them sort of on all stages. As I said, there is the issue, of course, that you have to have enough data to actually do this. And you have most of the cases to provide, specifically for text problems, you have to provide human input to generate training data, sort of to qualify a piece of text to be I don't know, a customer who is angry because a product didn't work as expected or whatever. So someone has to read these messages, then they have to associate a specific feature that is relevant, and that you have to do over and over again until the model can do a reasonably good prediction. Once you ended up having a model doing this, of course, because you have typically thousands, if not hundreds, thousands or millions, or in the very large models, even hundreds of billion features that you need to process, especially in language. The reason is that language can in principle be seen as an open system. So there are so many words, and there can always be new words. So if you want to capture the characteristics, the semantics of that language, you just need enormous amounts of examples. So what we see here is that, in my opinion, we are facing an architectural problem. So we have stagnating computer power, and the only way in getting more complex models to be trained is to provide more data, which leads to more computer power and so on. And the question is this efficient, and will it be efficient enough to actually become useful? So that problem is basically, and I tried to bring up a sort of a metaphor of a car that works based on water. And on the left side, you see one implementation of that. where water is actually used as steam. And on the other side, you see sort of the latest principle, namely bringing car and water together around the hydrogen fuel cell, which is precisely much more efficient and has a lot of advantages. So the sort of question I'm after is, at what fundamental level do we need to change parts of the architecture of the approach per se to sort of bring efficiency back sort of on the road again? Because by just building bigger and bigger steam-based cars, that's not the way to end up with the most efficient use of this. So the problems in this, I called it typically statistical modeling, by getting features and just multiplying your way through those features, which ends up in huge computational effort to sort of mass combine all the data you have, which precisely leads to a very large combinatorial space, hence the computer power that's needed. So on the side of text, there is, for example, one quite famous example that came out from a scientific study where they tried to find out how well can you possibly find a specific document in a collection, given that you create a statistical representation of the text within this document. And interestingly, so what they did is actually they took very large collections of documents, specifically, I think it was patent documents mostly. They extracted all the terms that they found within these documents, and then they generated mass queries. So by basically taking all the terms, creating search queries with those terms, searching against the collection of patents, and measuring how well they actually find certain patents, and what combination of keywords that they extracted, what document pops up at the top of the list. And the very astonishing thing was that there was a huge blind spot that was sort of generated. So the bigger the collection actually, the bigger the blind spot becomes, which basically means that there are a large number of documents where whatever combination of keywords you might come up with, you never get them to end up very much on the top of the list. In fact, the study precisely found out that in some applications you could sort of delete 80% of the data and people would not notice it. And that just shows the limitations of applying statistics to something like language. I mean, language is statistical to some degree, no question, but it's not, you cannot fully describe language using statistics. And that's where you actually sense this. And so just as an example, what we have with a huge index, like for example, Google, is that we have the impression, as we always get answers, that we have the power sort of to search through the data, but in reality there is an increasing amount of data that is in the background, which cannot by any technical means be reached, other than knowing that it's there in the first place, which would make searching obsolete. So the von Neumann gap, which is sort of the principle I described earlier, if you now compare the increase of the processing power with the increase of data that's available, you see at some point that there is a gap which definitely doesn't look as if it would be closed by any time soon. Another aspect that is related to statistical modeling is, of course, like a secondary effect. If you need a lot of computing power, you need a lot of energy. And I spoke to a number of people just to find out that it's very often underestimated how much energy our computing sphere actually uses currently. So if you take together all the digital devices and their energy consumption in the information sphere, sort of globally, then already today, so in that term, the number actually comes from 2018. We are using for the computing sphere as much energy as we use for the global air transportation. Which happens to be around 4% of the global energy. So this is not just a sort of small part of the energy consumption, which is minor compared to any industrial and other activities, but this is really one of the top factors that we should take into account when it comes to energy consumption, especially if you see the growth rate and you find out that if we continue as we do using energy, and I would even say it's probably not a linear development, it will be more towards an exponential growth that we will see. But even if it's linear, we have to be prepared that we will have like 8%, like a doubling of the energy that's needed for the information sphere, sort of, which would correspond actually to all the automobile transportation on the planet. And just again, from the bird's eyes view, all the industries currently facing the global warming issues and so on are trying to get more energy efficient. And the only sort of big industry that obviously goes completely in the other direction is the computing industry, if you want, because we haven't found any way of being more efficient than mass combinatorics when we do modeling, which actually leads to that amount of energy. And then last but not least, the way we do machine learning currently is actually to train a model that is very specific to one specific problem. And each of the models, each of the network architectures and so to be trained, they are very local. So you have to have local examples of local data and you train a local model which is then used locally. And if you extrapolate that, we will end up in what I would call a million model multiverse, basically a completely fragmented environment where basically every user of every application uses a very specific model with all the problems of updating it and handling it and so on, which again, the problem is you cannot generate network effects anymore at that level. And this has been, from an economic standpoint, a very strong driver over the last 20 years or so, that the network effects precisely are the ones that create the big money around those innovations. So the impact that this has, if you want, at the society level, and this is just supposed to be examples, sort of, where this can lead, is that, for example, the findability issue, making it hard to find information, also makes it hard to find true information compared to maybe artificially propagated fake information. So fake news has a much easier time when finding is not so easy. The von Neumann gap, of course, very obviously is a big counteractor to any effort to cope with climate change. The whole point of creating statistics, which in the end leads to averaging to some common denominator, even if the denominator is very complex, of course makes it hard to become aware or to handle cases which are special cases or more extreme cases. And so a whole economy that is just focused on averaging everything to the maximum to sort of get the biggest impact might turn out to be problematic. And the only data that is really there in endless abundance is actually data about consumers and how they behave. And those consumers, they are just people. They are the elements of the sort of civil organization. And if they are the only ones that are sort of perfectly modeled because they have endless data, there is, of course, the danger that people with enough sort of motivation, let's say, can actually train those models to sort of know more about the people than they might know themselves, and with all the consequences in this. So the approach we wanted to take with this is to go down to a very fundamental level and try to find alternatives. And one area where it's always to have a look at is biology, because biology and evolution are definitely systems and sort of environments where everything is focused on efficiency, because that's what, for a living organism, energy is the most precious resource. So evolution basically made organisms survive that do whatever they do with the least energy to use it, basically. And the human brain, of course, works along the same principles. And already in a human, humans who are doing what they are doing, using their brain and their intellectual capacities, and doing this with energy levels of something like 15 to 20 watts, which is ridiculous compared to even a single microprocessor. You see how efficient it is, and still it is sort of the highest energy consumer in the human body. Compared to its weight. So it's an interesting mechanism. So the way how we try to overcome this is precisely not to try and optimize and increase the algorithms, but to rather focus on the representation. And what we ended up with in our initial research is a representation that has been modeled along the representation of data in the human neocortex, where actually thinking happens. And I won't go into much detail here, but what turned out to be a key issue is that computation is actually making analogies when it comes to concepts and language use. And those analogies can be calculated in the easiest way if you have two representations, and you can literally, by comparing feature with a feature, sort of find out how similar they are. So we have developed a technology that is able to convert any piece of text into what we call a semantic fingerprint. That's one of these squares that you see here. And the rendering, the distribution of the dots in this square, so these are binary two-dimensional vectors, and the distribution always corresponds to the actual meaning of what the fingerprint has been taken. So if I take a fingerprint of the phrase signed contract and another one of the phrase done deal, and I do this based on a language model that is specifically trained on the language that business and economic people are using, we find that those two sentences, although they are not sharing any word, have an overlap of 36%, which is quite substantial. So they are nearly meaning the same thing. If in contrast I change one side to the phrase Star Trek, that overlaps. You can literally see by looking at the fingerprint representation how different they are. And just sort of as a high level comparison, you could imagine one of those fingerprints to represent the part of a human cortex, and wherever there is a dot, the according area in the cortex is actually activated, and that's looking extremely similar to actual pictures people are taking nowadays with brain imaging techniques while exposing people to concepts. They can literally see on the fMRI, for example, that they have specific image distributions and patterns for specific meanings. So there is a very close relationship. Nevertheless, although we are doing all of that without using any floating point, without doing any massive matrix multiplications and so on, it turns out that we can achieve with a much lower use of computing resources the same levels of precision. And those levels of precision compared to statistical models can be achieved for not the fact that the algorithm we use, which is basically Boolean operators on those fingerprints, they are not more precise, because in the end, all of these modeling techniques have at least the potential to reach very high degrees of precision. The reality is that you can only reach the high regions of precision if the system is efficient enough to allow you to do a large enough number of iterations and refinements. So an algorithm that theoretically can achieve 98% precision, let's say, but that takes 2.5 months and $5 million to train, and that's not overstated. I mean, that's where currently probably the state of the art in language modeling is. Then, and you would find out to actually tune the system properly, you would refine that, let's say 10 times, even if to take a small number, you see that even with that 100% inefficient system, it will take forever to actually go there. Our language models, for example, compute in about 1 to 2 hours on a laptop. To compare that. So that is the actual advantage, not so much what the synthetically measured precision would be, but how well can I actually achieve that precision in the real world. So to sort of round up the thing, why high efficiency, I think, will play a very important role in the future, is because only if we become more efficient, we can easily scale up, and hopefully once again in a more linear fashion, scaling up in a more linear fashion, which I would call sort of semantic supercomputing, to figure out the meaning of all the data that's out there. So this is in some terms not even limited to language only, but basically to all data, because all data has a meaning, and it would allow us to include that meaning with the data. The other extreme, if you have a very lightweight and powerful implementation, is that you can scale down. So you can create edge systems that already sort of do a bulk of the sort of applying the model where the data actually occurs, instead of feeding it back in some cloud system and so on. And then the other aspect, of course, and I've spoken about this in the panel already, it would finally allow us to sort of separate out the actual functional solution from, for example, the language in which it is applied. So currently, very often, we have to reinvent a certain language AI function separately for every language. Which is, of course, cumbersome. It would be much better to develop the application on one end and then to plug in different language models, and the system would behave exactly the same. And last but not least, if this whole computation becomes more lightweight, it would allow us to zoom in more specific areas. So a problem that we see today very much in legal document processing, for example, is that all the documents are basically using all the same words. Yeah, so it's very hard to differentiate. And only when we bring in semantics in addition to the statistics, we can be able, like humans do, by the way, in much more clearly discriminate between two pieces of text that are basically written using the same vocabulary, but meaning different things. So that's what I would call hyper expertise. So that people who are highly specialized in a very specific domain, for example, still can have useful and strong search systems within that domain, differentiating at the very fine grain level. Yeah, so that would be my 30,000 feet view on the topic of high efficiency AI.